Hi everyone, welcome back to my math channel online today. Today I'm so exciting to show you I am in a happy mood. Anytime like the weather is getting better, we don't have a rain and then I feel better too. So um, I would like to get into the problem today. Um, this problem is connected to the previous problem in my previous video. However, it's slightly different. It more information given, and mm, we will solve uh, the displacement of the spring in the equilibrium system. So I have one problem on the board. Let me read it out to you. A spring with a mass of 1 kilogram has a length of 0.53 meter. A force of 4.25 Newton is required to stretch it to the length of 0.7 meter. If the spring is stretched to 0.66 meter, then release with a downward speed of 2.1 meter per second. Find the maximum displacement of the mass. So it sounds a little bit complicated, but let me draw the diagram to demonstrate what is said here. So we have a spring with the bar, and then the spring attached to this bar. And this spring have a length of, so at this level, the spring have a length on the way from here to here is 0.53 meter. So the length of spring is the length of spring is 0.53 meters. So from here to here, right, is 0.53 meter. A force of 4.25 is required to stretch it to the length of 0.7 meter. So let's say the spring is stretched to the length of 0.7 meter. So at this level is 0.7 meter on the way from here to here. So this spring is supposed to be stretched, and I put a dot to show that you see a natural length of the spring. It should try to stretch up to here. Okay. If the spring is stretched to 0.66 meter, which is less than this a little bit, so let's say if the spring is stretched up to here, and at this level is 0.66 meter, then release with a downward speed of 2.1 meter. So if it's stretched and it release, so it release at time here 0, it release with a downward speed of 2.1 meter per second. If the spring is stretched up to here, then release with a downward speed of 2.1 meter per second. Okay, so here then it release. But the speed, the velocity equal 2.1 meter per second. Now, because it says downward, so I'm going to put the direction negative. find the maximum displacement of the mass. Okay, so let's talk a little bit about the any equal force. This is apply equilibrium system, which is apply the Newton's second law, which is any force have an equal reaction force, right? So if I punch my hand into this bar with a very strong force, then there is a force hit back to my hand, and that's why I got hurt. So if I punch it so strongly, then my hand gets more hurt. If I punch with the lighter force, softer force, then my hand doesn't get hurt much because the reaction force to my hand is not much as well. So now we see the any force have an equal reaction force, right? Well, it's true. Now, in Newton's second law, because of that, so we know that if we stretch the spring, the force pull it down equal the force push it up, right? And therefore, the equal magnitude get the spring go back to the same initial position. However, in this question, it say that we try to stretch it with the velocity. So there is a fast velocity involved in the motion of the spring, go fast, go downwards with the speed of 2.1 meter per second. So when it rises back up, any force have equal reaction force. So we're talking about the opposing motion in the spring go back up. And the question asks, when the spring go back up, what is the maximum level? Because the spring will pull down with the velocity of 2.1 meters per second. So when we release it and the spring go back up, of course, if you stretch it strong, it will go back up with the same magnitude and stronger. So it go back to the maximum level stronger and maybe higher. But if we spread the spring, it's slow with the lower velocity. When it go back up, maybe the maximum displacement will be lower. So that's the scenario we were talking about the spring. So the questions say, what is the, let's say the scenario, the situation, what is the maximum when it go back up? Because you know any force have an equal reaction force. So this is the pushing down, but there also the vector force going up, right? So what is the maximum level when it go back up? Where's that, right? Maximum level. So that's the scenario. Now we understand the scenario. Now we're going to talk into how to resolve it, how to solve this problem. So remember Newton famous for his equation. Like I remember Albert Einstein famous for his equation is E equal mc square, and Newton famous for force equal mass times acceleration. So E like energy, mass time with the speed of light. Each great scientist have one equation for us to remember. So Newton famous with force equal m times a. So force equal m times a, mass times acceleration. Now, in our scenario, we can express this as force times with k times with s. S is the spring, right? The speed of the spring, velocity of spring. So force equal k times s. So our first task, so step 1 is to find k. So we want to find k, we substitute in this equation, and our number to substitute is force equal 4.25. So I substitute this by 4.25 equal k is what we want to know. And remember the s here is the delta s, right? So this is delta s. And delta s equal S2 minus S1. So in our case, S2 is the spring is stretched. It's required to stretch it to the length of 0.7 meter. So 0.7 meter minus 0.53 meter. So that will give us 4.25 equal 0.17, I think, but make sure it's accurate. 0.7 minus 0.53 equal 0.7 minus 0.53 equal 0.17. So now to solve for k, we divide both sides by this number, 0.17. And now 0.17 divided by 0.17, gone, equal 1. So this number equal k. Let's check. 4.25 divided by 0.17 equal 25. So 25 equal k. So now we know k. So now we put in our differential equation is the second derivative. Let me write in this form first. Remember, this is the differential equation and in the equilibrium system. And the reason because we have an equilibrium system because any force have equal reaction force, and the force have a direction. So the force go to from my right hand to the left, and equal at the force go from my left hand to the right. So they go different direction. It means one positive, one negative with equal magnitude, so they cancel out. And therefore, we have equilibrium system on the right-hand side equals 0. So if this number is positive, this number is negative, and they same magnitude, 5 minus 5 is 0. 6 minus 6 is 0. So that is just it mean, right? So now we can write this as d squared s over dt. That's a derivative, adding with k. However, we have to divide by the mass as well. K over m times with the s equals 0. So we're going to substitute this equation. Let's substitute this equation into the number, right? So I'm going to rewrite this d squared s over dt equal plus our k is 25 divided by the mass. The mass is fortunately is 1 kilogram, so it doesn't change. If we divide by 1 kilogram, it's just 25, right? And time with the function s. And this s is delta s actually, right? Equal S2 minus S1. Okay. So now, what else do we do? Just to remind you a little bit about the previous lesson. We say that the theorem, right? There is a theorem say that if we have a differential equation as it in equilibrium system, then there exists a y function, the orthogonal function, in the formula of our y is s in this case, right? Equal A cos of square root of k t adding with B square root of B sine, which is the trigonometric function, sine of square root of k t. Now, we already went through how to prove this formula is correct from the previous lectures. So in this question, we just use this apply to solve the problem. We will not bother to go through to prove the formula anymore. If you want to, if you are curious and you want to know, you can rewind my YouTube video from previous lecture. I has shown you how to prove the formula. That is true, right? From the theorem that if this, then this, if this, then this. So if we have a differential equation as it in our equilibrium system, in this pendulum pattern or in the spring pattern, we have this formula derived from that. We accept this is true and we already prove it. This is the formula. So now we're going to use it and solve it. Now the S here is a delta S. So our delta S in this case is if the spring is stretched to 0.66 meter, then release. So let's find delta S, right? Delta S will be equal 0.66 meter minus 0.53 meter, which is 0.13 meter. Yeah. So we substitute the S here by the number we know, 0.13. Our second step is to solve for A, right? So I'm going to write here so that you remember. So the second step is find A. And the third step is to find B. So let's substitute this by 0.13 equal A cos. Now at the time when the spring, remember what we try to solve is we try to solve the maximum level when the emotion in the opposite direction. So at this level, we assume the time t is 0 when we release the spring back up. So the time t, so t equals 0. So now we substitute the square root of 5, square root of k is square root of 25, which is 5t. So let's write out the formula first, okay? Just be careful. So I'm going to write out this is A cos of 5t because square root of k is 5t, adding with B sine square root of k is, 5t as well. So now we replace this by 0.13, which is this number, delta S. And we know that when we release at the time t equals 0, so cos of 5 times 0, adding with B sine of 5 times 0. Now it turned out this will become 0, and we know in trigonometric, let's remind you a little bit, if you put this in the quadrant, you learn math 12, you know this coordinate is 1, 0, and this coordinate is minus 1, 0, and the coordinate here is the cos. And at this level, our degree is 0 degree. Then go all the way through back to 360 degree. So at this level is 360 degrees or 0 degree. So 0 degree, the cos equal 1, right? Look at this number, the cos equal 1. Or you can use a calculator to check that. So this become 1. The whole thing here become 1. 1 time with A is just A. So A equal this number. So now we know A. A equal this number. Now for the sine, again, you know this is 1, 0. So the sine here, if its angle is 0 degree or 0 radian, this is 0. So sine of 0 is 0, and anything times with 0 is just 0. So the whole piece here will gone. So now back into our function, we already know the A. Now we're going to find the B, right? That's the next step, find B. Now to find B, we remember from the previous lecture, I told you we will use velocity to find B, which is ds over dt, right? And our ds over dt, we'll let do that. ds over dt is the derivative of this original function, right? So now we're going to take derivative of this. Derivative of cos is minus. And remember, we have a phi. So inner, if we take derivative inside, will be minus phi. Time with the cos become the sine. And actually, we have A in here as well, right? And time with derivative of this is sine of phi t. Adding with B, derivative of sine is cos. So B, cos of phi t. So now based on this derivative, we're going to find B. And we know the information say the velocity is 2.1, minus 2.1. So we're going to substitute this by minus 2.1. And we're going to solve for B. So this will be minus 5 times with 0.13 sine of phi t. We were talking about what is the question asked, what is the maximum level if it were pushed down with the velocity of this. But when we release, remember, when we release the spring from rest, right? And when we release the spring from rest, the time is also equal 0. So we substitute the 0 in here, adding with B, and actually that should have a phi in front as well, phi B. So phi B cos of phi times 0, okay? So now let's check what is this number. So phi times with 0.13, it equals 65. So minus 2.1 equal minus 0.65 sine of phi times t, adding with phi b. Cos of phi times 0 is just 1. So it's just adding with phi b. And t here should be 0 as well. So what is our next step? We substitute velocity in here. Our velocity is psi of phi t, and psi of phi t is 0. So this will become 0. And our b, our phi b equals this number. So we have minus 2.1 equal phi b. Now we want to solve for b, we divide this by phi and cancel that. So 2.1 divided by phi equal 2.1 divided by phi equals 0.42 minus 0.42 equal b. So now from this we know b. Okay. Remember psi of phi 0 of 0 equals 0. So the whole thing here equals 0. And we solve for phi b, we get b equal minus 0.42. So now we know b and a. We're going to rewrite this equation again. So ds over dt equal, follow that, minus phi times 0.13 psi of phi t adding with phi b, and b is this. So phi times with 0. Actually minus 0.42 b, and b is this number. So we substitute that, right? Cos of phi t. Okay, so if we solve our velocity equation, we will get the angle, right, of phi t. Remember, this is just represent the angle, right? Phi t is represent the angle theta. Now, to solve this equation, we need to have left, right, and right side, left side and right side. So what is our left side? We supposed to put in here. Now, the velocity of minus 2.1 meter per second will allow us to solve for B. But the question now asks for the maximum displacement of the mass. So to find the maximum displacement, right? Let me erase this so that I have more room to talk about that. So to find the maximum displacement, we have to relate back to the derivative formula. Remember our derivative, let's say you have a function and this is the maximum, right? Maximum. Now, anytime you have a maximum, you have a tangent line, and the tangent line stands for the slope of the function at that point. And at this maximum point, our tangent line obviously look like the slope of it is m equals 0. So anytime you have a minimum or maximum, right? It's the minimum, same can happen. But here we're talking about maximum, right? So to find the maximum, we have to find the derivative when the tangent line of the slope of the tangent line equals 0. And the tangent line is the derivative. So this derivative, ds over dt, to find the maximum, we set this equal 0, right? And this is our derivative function, right? This is our derivative function, ds over dt. And we already know A, we already know B, so what we do is substitute the B and the A into here. So at maximum level, the derivative here equals 0. So we set left side equals 0. Now we can solve this equation. because if the equation doesn't have only have one side, it's not the equation. It have to have two sides. And the numerical 0 is perfectly a number. So now we have left side, we have right side. We are allowed to solve for it. And we be able to solve for the angle phi t here, right? To figure out. So let's figure out what is our angle phi t when we solve this derivative function. So because this is 0, I allow to move this root to the other side. So I'm going to move this to n minus phi times 0, 1, 3. Let's do that. So phi times 0 0.13 equals 0.65, and it's supposed to be negative, right? I just didn't put in the sign, but that is the value. And now I have to move this over. So when I move this over, this numerical value 0.65 will become positive. So I'm going to put here 0.65, 0.65 positive. Sine of phi t is the angle theta, right? This represents angle theta in trig. This is also minus phi times 0.42, phi times 0.42 equal 2.1, so minus 2.1 cos phi t. And at this point, how do we solve for this? And actually, I forget the equal sign. That's dangerous, right? That should be minus 2.1 cos phi t. So we have a left side is this one, and the right side is this one. Now I'm going to manipulate a little bit, right? I am going to relate it to the tan theta. And how do I put tan? To get tan, I have to have a sine over the cos, because that's tan equals sine over cos. So I'm going to keep the sine here, and I bring the cos over. So multiply become divide when I bring it to the other side, right? So now if I bring it down here, this gone up top here, right? To keep the number on the right side, I'm going to bring this number, I'm going to kick this number down here to the right hand side. So I'm going to divide this by 0.65, and of course this gone. So I ended up this root equal this value. And this root is 10 of phi t. 10 equals sine over cos, right? So 10 of phi t equals this number. Let's figure out this number. Divide by 0.65. So this number is minus 3.23. So on my calculator, that's the number look like. I draw it up. So 3.23, let's draw it up one more level. So now I have to find the angle theta of phi t, which is, I will put in the program of our calculator at the second level reverse, like 10 minus 1 of this ratio to figure out our angle in radian. Make sure you put your mode in radian, right? Mode when you do this type stuff. So now I'm going to figure out, I'm going to hit second 10, right? I'm going to key in minus 3.231 and I'm enter. So I got this number of the angle phi t is minus 1.27. So this equal minus 1.27 round off is radian. Remember the value here is the radians, not the degree value, but the radians value. So make sure you distinguish. This is the ratio we put in, and this is the radian come out as the outcome. So we know this angle, right? And that angle look like, now remember in trig, this is 6.28, this is pi 3.14, and this is 1.57, and this is 4.17, and this is 3 something. Yeah. So minus this will go down this. So the angle is maybe around here, because that's minus 1.271, right? So that is something like that. That's the angle theta, okay? In trig, in the quadrant, you can draw like that. Anyway, I just demonstrate to you to see the location of it. It's nothing to related to this, okay? Now, so after we get phi t, we know the angle, and this equal phi t, angle theta. Now we're going to put back, so our displacement function back into our displacement function in this formula, which is this one. You see our displacement. We want to know the displacement, we have to use the formula of displacement. And our formula displacement is A, which is 0.13 cos of phi t, adding with B, and our B is minus 0.42 sine of phi t. So let's find out what is our displacement. So our displacement will be cos of phi t, which is cos of minus 1.271. We know the angle, right? Minus 0.42, and sine of this angle, which is minus 1.271. So now let's key in calculator on it one, see what it will be, okay? So I have 0.13 times with cos of minus 1.271 minus 0.42 times with bracket, time with sine of minus 1.271. Okay, so this is how I key in exactly whatever we have on the board. Let's hit enter and find out. So the answer is 0.439. So the answer is 0.439, 6589. 6589, blah, blah, 279. Now this number can be drawn up, become 0.44 meter. So now we know the displacement of the spring mass when it goes back at this level is 0.43 meter. So we have solved this problem beautifully, isn't it? So let me see. Because this is a complicated problem, so I'm going to summarize for you a little bit. So first, we have a scenario of the spring, and the natural length of the spring is from here to here, 0.53 meter. Then it was stretched up to 0.7 meter. And when it's stretched up to here by the force of 4.25 Newton. So the force of this stretch happened when this vector force equals 4.25 Newton, okay? So we know that if we spring the spring down, but the question asks, if the spring is stretched to 0.66, so If it's straight up to here, not down here, not up to 0.7, then it releases with a downward speed of velocity equal minus 2.1 meter per second, right? If it's straight and release, straight with the downward speed of minus 2.1 meter per second, when the spring is released, it go back to the maximum level, right? Because any force have equal reaction force. So it's pushing down, there's a, when we release, the spring go back up. And how far it go back up actually? This is the question, the maximum displacement of the mass. How far it go back up? Does it go back up right here, or go back up here, or go back up here? Now the reason it happened because in here we have to push the force, and we exert a force to make the spring have a motion of the velocity, right? So it go back, it not go back to initial position because the speed happened to make the spring go back up. Okay, so it's different from the previous question, quite different, right? Scenario. So after we understand the scenario, we now follow the formula we already proved. If there is a differential in the equilibrium system happen, if there's a y prime, right, y2 prime, then there is at least a original function with this formula. And our task is to find k. The first step, we want to find the k value to put in here. So that's the first step. And the k value based on the force equal mass k times s. So if we plug in the force of 4.25 equal k times delta s, then we'll be able to find k. And our k equal 5. Square root of our k equal 25. But divided by the mass 1 is just 25. Square root of it is 5. So we have the formula of S equal A cos phi t plus B sin phi t based on this formula. So now we solve for A. Next step, we solve for A and solve for B. To solve for A, we put in the delta S, the displacement, when the spring is straight up to this level, not this, 0.66 minus 0.53, the natural length of the spring. Then we know the S here is the distance of that, and this equals 0.13 meter, equal A times with cos of phi times with t. We substitute t by 0 to find A. The reason because at the time when we release the spring, the time equals 0. So yeah. So now after we substitute, we find A, we got A 0.13. Then we use the second derivative. So we have to come up with this equation from the second derivative, which we take derivative of this original function, and that equals this function. So now after we take derivative, then we'll be able to substitute the derivative numerical. They give us this data in here to find B. And it turned out when we release the spring, the tie is also 0. So we substitute tie is 0. So this will be gone, the whole thing gone. So we left with phi B because cos of phi 0 is 1. So we left with phi B equal minus 2.1. So we divide by phi to solve for B, we get minus 0.42. Now we will have to figure out the question, the answer for the question, what is the maximum displacement of the mass? So to find the maximum displacement, we relate it back to the slope of the tangent line for the maximum level is equal to 0. So therefore, at maximum level, we are allowed to substitute the ds over dt here equals 0. And all what we do is put the numerical in and find out the angle. So after we find out the angle in radians, we got this value, right? And then we go back to the displacement because the question asked for displacement. So we put back our numerical value, whatever we know, into this displacement function, right? Not derivative function, but displacement function. So we use this, we substitute whatever we already know in the equation, and our answer is 0.44 meter. So I have proved to you, I have shown you how to solve this lesson very clear. Also, I already summarized back to what step we done for you. I hope that you'll be able to follow and understand this question very well for now. So I hope you enjoy my video today. It seemed that I wasn't talkative too much today. I just focused on the problem. Maybe that's a good sign. So anyway, thank you for watching and stay tuned for our next lesson. Our next lesson will be the iteration, which is the next chapter, the next unit of our course, second course in calculus. And this next unit is about iteration. So then stay tuned for the next video. We will talk about the iteration. And I would like, before I go, I would like to again introduce you to my math website, which is a beautiful website, my math teaching. And if you can Google, it's very easy to remember. Just mymathteaching.wordpress.com. And you will see the beautiful website to show you. So anyway, thanks for watching and bye for now, and see you in the next video.